We do it, for example, with zirconium, and it goes up to 100 or 100 eV. And so this could easily be 100 electron volts up here somewhere. This is meant to be an illustration. Okay, I will go forward. So that's measurement. Now I want to talk about pulse selection. That came up slightly in Ken Schaefer's talk, and so you know some of the ideas. The very first method for selecting an attosecond pulse from the train of attosecond pulses that are high harmonic was just to take the pulse and sculpt it as best you could. Well, maybe Ken Schaefer said that that wasn't the first, but that's what was thought to be the first, aside from what Ken Schaefer said yesterday. So, and this is still the route used in some places. So the idea, a bit like you heard yesterday, but let me review it quickly. The idea is that if you have a pulse that's perfectly reproducible, shot after shot, you can easily get to a situation where one peak is not sufficient to ionize, so there will be no high harmonics. The next peak will ionize great, so let's say that one will ionize. The electrons will be pulled out, be brought back at high energy collide, giving high energy photons. So there it is, a burst of high energy photons. The next peak will also ionize well, but of course the electron will be pulled back very weakly and collide feebly, giving you a low energy burst. So you might have two bursts of attosecond pulses, one high photon energy, one low photon energy, and a filter picks out only one pulse, spectral filter. That's what Ken Schaefer talked about yesterday, just to remind you. And that was the first method used, and it was used in the experiments that were originally done in Vienna, and when Christ moved to Munich, I think that's the method they used. A second method that probably more commonly used now is, well, it's a combination of two, and it starts with the polarization gate. So let me stop for a moment and talk about this, because I think the image is not very clear. Okay, so I asked you to calculate trajectories, and you heard Margaret talk about a little bit the trajectories with circularly polarized light. If you have circularly polarized light, electrons never come back and collide, they just go off to infinity. So you might have calculated that. So if I have a pulse whose polarization changes from circular through linear back to circular, the circular part can't do anything, the electrons go away. At linear they can come back and collide, and then if it goes back to circular, they go away again. So this becomes a gate in the pulse, and only those electrons created right near linear polarized light have a chance of colliding and giving you a burst. And if you do this well, you can make that gate so short that it's a fraction of a cycle of light. You can only allow one fraction of a cycle. The pulse will still remain short, but it's a more forgiving process than this, and it doesn't require a filter. In other words, it happens across the full spectrum, or very close to the full spectrum. So polarization gating is just using the exquisite sensitivity of high harmonics to the polarization of light, as you will have worked out last night in the trajectories in circularly polarized light and linearly polarized light. And if you're not sure about it, go back and try it in elliptically polarized light, and you'll see that the offset is still significant. Let me just comment about the third one, second harmonic generation, two-color light. So if in this case you take two colors of the same polarization and you phase them as they're phased in this diagram, I don't know if you can see it well, there's a blue there and the red there, and they're organized in such a way that the superposition of the red and the blue gives you the peak up there, and it gives you a valley in here, and so it makes the time-dependent field as far as its magnitude quite asymmetric. So that really turns off this highly nonlinear tunnel ionization, or it can in one half cycle and just bring it so it can only happen in once per cycle instead of once per every second, twice per cycle. And so that means that the attosecond pulses that you could create can only now come once every cycle instead of twice a cycle. That would change the harmonic structure, and it does. But it also makes the gating a lot easier because now you only have to forbid it from colliding once per cycle instead of every half cycle. And so putting these two together is called double optical gating. Double optical gating because you use two different processes. And this can be slightly improved, but this is quite a common technique now. In my laboratory we use polarization gating some, but I want to describe a third process. And I thought about which one to describe more carefully. I described this one because it's quite different. It also complements what Ken said yesterday, that spatial aspects are very important, or can be very important. And so I want to talk about using a space-time coupled pulse. Before I leave that, I want to say that these three processes, the way I've described them, all work on every single atom the same way. That is, if I make the electron miss on one atom, every atom it missed on, or to a large probability it missed on. And so it happens on a single atom level. What I'm going to talk about here, this new kind of technique, which is called the lighthouse, doesn't work on each atom, but it works on the full beam, but it has much the same behavior. So I wanted to use an example to show you an isolated pulse, how they're created, and then I'll show you a measurement. So let me give you the idea. The idea is really beautiful. That's one of the reasons I wanted to do it. The idea is due to Fabien Carré, and we worked almost immediately with them to put this into practice in gas harmonics. So imagine you have the perfect femtosecond pulse that you could imagine. Q cycle, femtosecond pulse. You get everything together, everything going perfectly together, and the last thing you would ever think you want to do is put it through a prism ring. Every color start to spread out. It's just an elementary bad idea for a short pulse. So, but if you put it through a very weak prism, each color begins to separate, focus them, and in the far field, you have a separation between the colors. Now don't make it so big so that they truly separate, but make it so there's a bias towards the blue on one side and the red on the other side. Normally you wouldn't do this, so this is a space-time coupled pulse. Think about what it looks like now when you think of it in time. Here are the oscillations sketched in the figure here. So I'll just connect the peaks and the valleys, and you can see that each half cycle of the pulse, the wavefront rotates. The wavefront rotates just a little bit, but it rotates a little bit, and attosecond or high harmonic radiation that's created is always created perpendicular, essentially perpendicular to the wavefront. And so it will go off in a slightly different direction each time. In other words, the train of attosecond pulses you create, each atom would be a train as if it saw the full train coming in. But when you take the full beam together and you think, what is emitted, what comes out phase match, they come out in slightly different directions. So it makes multiple pulses, naturally called probes, and things like that. So it seems very useful for applications in this kind of a neat way. And like I said, I thought I would show you that. Here's an experimental example. Here's a few cycle pulse coming in, creating a set of harmonics with no space-time coupling on the beam. In other words, the prism's removed. Here it goes through a weak prism, creating a set of harmonics, each going in a slightly different direction, where this is the direction, or the momentum, or the angle in which the beam is going, and this is harmonic energy. And these harmonics are created, I believe in this case, in argon, maybe neon, but argon or neon. Probably neon. It must be neon. So you can see the isolated pulses coming, each coming in a different direction as each half cycle goes by. Actually, they're more isolated than they look. Actually, there's some modulation, so there's a bit of overlap. The modulation tells you the degree of overlap, so at 1%. And there's a bit of jitter in our the carrier envelope phase, and so that makes the overlap look worse. Okay, so we said let's set up and bring these through an aperture so that we can send this off to a detector and reconstruct the photoelectron energy as a function of time in attoseconds. And so I'm going to show you 3 images. I show you here, but I'm going to go right away to the next one for one pulse, the next pulse, and the next pulse. You can see the images of how we're going to do it. And they're going directly into a streak camera. And here is the streaking traces, right here. Spectrograms of each of the 3 pulses, one after the other. Each of the 3 attosecond pulses, separated in slightly different directions. From now on, they can be handled independently and set up in Pump Pro, do phase-controlled experiments or whatever you wish. This is the photoelectron energy, which is very close to the photon energy because it's a photoelectron replica. This is the time delay between the attosecond pulse and the infrared. So just delayed in the delay line that you saw, measured in attoseconds, and this is just a calculation. And these are all done for the beam going through an aluminum filter. And the aluminum filter restricts the bandwidth of the beam to something that is 80 eV in photoelectron energy. You can see that restriction. This is not ideally compressed. For the same experiment, you can put it through a zirconium filter. This is the zirconium filter. Here's the streak spectrogram, and here's the experimental pulse that we reconstruct in this case. We did not try to optimize it, but it's 130 attoseconds. Okay, so now that's one example of how an attosecond pulse can be selected from the training of high harmonics, and it's an example of how measurements of attosecond pulses are made.
Can you go back to the last page?
That one or
one later?
Later.
Yeah. Go from the top set of graphs to the middle set of graphs.
So how do you go? So this is the basic measurement. It is it's energy versus time, very much like frog data. You can see the oscillating field. Actually, if we went out further, you'd see the oscillating field dry off, go off, just to tell you. And so it's possible to go into an inversion algorithm, this is done iteratively now, into an inversion algorithm to reconstruct both the time-dependent field and the attosecond pulse, the pulse that's there. This is done, this is the detailed method within this is called frog crab. Everything has got these funny names of little animals. In this general area, I'm not sure why, but it's there and it's hard to get rid of. So it's called frog crab, but it's basically a frog technique. And frog is an iterative algorithm that takes this 2D information and reconstructs it along the pulse. So I can't give you a better answer than that because I don't think it's qualitatively accessible. It's just an iterative algorithm. You can show that it must converge, and that's what I told you. There's a theorem about this. And Ken Schaefer commented a little bit about that. I would point you to the theorem or point you to work on it, but I couldn't give you a qualitative image beyond that. But it can be reconstructed. And this is a calculation done with the strong field process. And this is the same. This is just happens with a different color. Okay, so if everybody's comfortable with the attosecond measurement, I'd like to say that as with autocorrelation Pump Pro, if we use a sample we understand, then we measure the attosecond pulse. If we use an attosecond pulse we understand and a sample we don't understand, then we measure the response of the sample. So I wanted to give you an example of that, and it's not from my laboratory because I did this experiment in my laboratory. But here's an example coming from the laboratory again of Ferenc Krauss in Munich. And in this experiment, the experiment used an attosecond pulse to come in and irradiate a sample of material, a metal sample. I think it was a titanium sample. I thought I'd written it down here, but since it's not my experiment, I don't remember for sure. But he irradiates a titanium sample. You create photoelectrons from the titanium sample. Now they can come from one shell or another shell, creating photoelectrons at different energies because you need different energies inside the system. And now you do a streaking trace by bringing radiation into the surface of this and streaking the photoelectron as soon as it emerges into the continuum. And so here are the streaking traces. You sort of recognize this oscillation as you vary the delay of the infrared laser doing the streaking in this experiment. It's Ti-Sapphire, 800 nanometers, and the time scale is there. And the same thing you can do with the electrons from the deeper bound state, deeper bound levels in the titanium. And so you can see a slight time delay. If you look at these oscillations, you can see a slight time delay in one versus another. A time delay in the emission of electrons, very small. It's only a few tenths of attoseconds. And there have been many replicas of this experiment. This is the first, a few tenths of attoseconds. And these electrons then are released slightly later from the lower states than the higher states. What's the cause of it? Why is that the case? It's not clear. It's a lot of experiment, a lot of theoretical work, and it's not my work, so I haven't followed it very carefully. So, the idea I liked was that it interacted with the plasma in a way that I'm not sure it is right. But I wanted to give you an illustration of how this can be used. And there's an array of these kind of experiments on atoms looking at relays, photoemission, and things like that. Okay, so to review, and I think I still have lots of time, don't I? Because I have another section I want to deal with. Okay, so to review, we now know how to make coherent X-ray pulses extending, what you heard from Margaret, up to a nanometer. We can engineer a single recollision and make a single sub-femtosecond pulse, and we have to measure with them, and we even begin to know how to use them to explore very fast phenomena that we never thought we could explore before. Now, yes, please.
What's the accuracy of the measurement? I mean, the pulse duration?
The pulse durations that, so I think I'm not sure you're referring to the specific non-interference curves, and I can't remember the pulse duration, but he works generally with 90 attosecond pulses. He would, the argument that he doesn't make explicitly in this paper, but implicitly, is that when you try to fit these oscillations, these frog-like oscillations, because you have a lot of information in the oscillation, you can fit them, centroid them, by using all of this periodicity, much better than the duration of the pulse. And so the measurement of time delay that they talk about is only a few tenths of attoseconds. And this is characteristic. Similar time delays are found in photo emission from different levels in atoms, for example. From one or another level, you can get photoelectrons that are labeled in their energy, and they're streaked in the field. And a number of people. I like this solid state one because I have no idea what it should be. I don't know how to calculate it. The atomic case you probably know how to calculate it. It's interesting. Okay, so I've set up perturbative nonlinear optics, extreme nonlinear optics. Can we bring them together? So I want to make an argument that we can. I think that's sort of an interesting thing to think about. And to a certain extent, you've already heard about this experiment, and I want to use this experiment as a start off. Margaret referred to it indirectly, not directly, just a minute ago. So let's try an experiment. Let's try an experiment in which we bring a strong infrared pulse, 800 nanometers, into a material. We create high harmonics in the material. The high harmonics go forward along this dotted line like before. And let's bring in a weak pulse from below, second harmonic, and perturb this. Just a little bit. You might think of it, one of the ways I thought of this when we started out, I thought an ionizing gas, which we create with this red pulse, this infrared pulse, if you think of them together, the intense rate radiation and the ionizing atoms, these are exquisitely nonlinear materials. And could I use that nonlinear material in a normal way with a weak pulse? Could I use it, or could I integrate perturbative nonlinear optics into strong field nonlinear optics and find a little bit of both and bring some of the techniques in from perturbative nonlinear optics? And I'm going to argue again. Okay, so what would you expect to see? So one way, again, another way to look at it, during the important aspect here, there's an ionization. The electron is pulled from the atom and driven back to the atom again. And the weak laser field, when it's there, will manipulate that electron when it's out, adding a little force, and if it's phased just right, it will add a little force, adding to the trajectory, adding to the phase of the electron. And because it's coming at an angle down here, it will be a different phase that it might subtract from the phase. So I will put a phase modulation across the recollision electron, and that phase modulation will be transferred to the radiation as before. Okay, let me make sure that it's clear. Think about the quantum mechanical way to think about attosecond pulse by harmonic generation. Electron is out here in the continuum. It's going out through its path. Its path is determined by the fundamental beam. You could move the arm of that interferometer. You could change the length of it by adding a second harmonic. Keeping the fundamental fixed, add a second harmonic. At some phase, the second harmonic would just add to the trajectory, add to the action, add to the phase when the electrons collides. 180 degrees out of phase, it will work against the trajectory and shorten it. It would be like taking a micrometer and moving it back and forth across the wavefront of your beam. So that's what we want to do. We want to manipulate that. And here's what happens when I do it. In this case, it's not a weak, it's a relatively strong perturbing beam, but I want to show you the pattern, and then I'll come back to it. So if there were no perturbing beam, here's the harmonic spectrum coming out here. You can see them, and they're labeled having 0 perturbing harmonics, and that's what they are. Now, because we have the perturbing field on, the perturbing field has made this grating, if you wish to think of it that way. And that grating leads to a diffraction, and we use a second color to do it, so it's clearly labeled. So here it is. This is the first order diffractive signal, in this case, and we know we've absorbed a photon. We've absorbed a photon because the photon, the beam was coming up like this, and if the beam comes up like this, the momentum carries it if it absorbs up. If it emits a photon, it carries it down. So we can tell if it's absorbed or emitted. We can tell that. Oops. So here we've absorbed a photon, and we know it's one photon absorbed, and we know it because of the color, and we know it because of the position up here. Or it could have emitted a photon, and there it is emitted, and so we know how many photons completely were involved in this process, in fact. And we can go up and absorb 2 photons, and 3 photons, and 4 photons, and 5 photons, and so on. And so these are infrared photons from the perturbing beam, which we use the second color so we know what it is, and that leads to this map that's created. But now I want to perturb this. Yes?
I've always wanted to ask this ever since I saw this paper. Have you cut off the lower end, or is emission much less likely than absorption?
It's not symmetric, or it's not always symmetric.
So why?
It's not cut up. Well, I should be careful in this case. It might have been cut off, but it's not completely symmetric always. I'm not sure why it isn't symmetric, actually. It's an interesting question.
All this way I came.
Yeah, okay. It's an interesting question. Experimentally, we have an aperture we go through for differential pumping, so this could be cut off from that aperture, and I'd have to ask the Julian Bertrand. I don't know.
Right, in other words, you only really have a clear shot at the up path.
But we could have made it so we have a clear shot in the lower path.
Yeah.
So I believe it's asymmetric.
What's the ratio between the strong and the weak field?
Oh, well, I'm going to come to that. That's exactly what just wait for 1 minute. That's what's so interesting about this. So, so now we have a way to say, just before I go to the next one, we have a way to say we've absorbed 1 photon, we've absorbed 2 photons, we've emitted 1 photon, we've emitted 2 photons, So let's take a look at it. Let's lower the intensity and see how it scales. Does it scale like perturbation theory? Because I said it was weak. Does it go linearly for 1 photon? Does it go quadratically for 2? Does it go like a cube for 3? Is there the right ordering between the two? Is the 1 photon more important than the 2 photon more important than the 3 photon? And the answer is yes. So here you see what happens. The weak field intensity shown here in 10 to the 13 watts per square centimeter. So this is 10 to the 13, this is 12, 10 to the 11, and so on. And here is the intensity of the signal creating absorbing 1 photon or lowering 1 photon. Now there are many signals that could be looked at because there are many of these diffracted beams, but they all behave the same way. So 1 photon process, well, there's the linear. I don't know if you'd say it behaves linear. There's the 2 photon, the 3 photon, the 4 photon, the 5 photon, and the 6 photon process. It follows perturbative-like behavior. The electrons are manipulated in such a way as to perturb, and the ordering is correct, the intensity-grade ratio is correct. And I think you can actually show I know you can show analytically that this should be correct.
And the turn off after you get past the behavior?
This is saturated behavior.
Saturated.
That's saturated. Okay, so that's perturbing it. So there are many things that come from this. You can begin to think about how to bring in all of the things from perturbative nonlinear optics for measurement. So some of my next part of my talk will be starting to bring in ordinary measurement techniques, and I'm going to apply them to kind of solids and to molecules. Okay. But there's another interesting thing. So if you assume a reasonable conversion efficiency of about 10 to the minus 5 from the fundamentals, and if you assume linear scaling of the intensity, and if you lock the signal on this curve at a certain intensity, and you project back, you can project back to say what would happen when I only have a certain probability of creating 1 photon in one of the deflected regions. Only a few photons in the perturbing beam are needed. We know when it's going to be, so they're going to be in a mode or in a time. Only a few photons in the perturbing beam are needed to ensure at least 1 axis photon in some harmonic. I think this means that ionizing atoms will have an interesting quantum optics. It will be an interesting Attosecond quantum optics. I think nobody has worked it out. If anybody has, I know of nothing done on it. I think it's a completely open field. It's using high-order nonlinearities. It might offer lots of interesting things. It's just a completely unexplored field, it seems to me. So you can think of it both either as perturbing this, or you can think of the material as exquisitely nonlinear, these ionizing atoms. So if I were starting out, I might start working on these scenario theories. I think it's an interesting problem. Now I want to use this idea, not the quantum optics part, because we have not done anything on it except talk about it in the lab. We've talked about different kinds of experiments and things you could do. But I want to use the idea in a different way. So I want to address an issue. Can we use these kind of ideas, taking a beam, bringing it in with the driving beam, perturbing the process, and using to manipulate the harmonics that are created? That's the question I want to answer. And to do it, I want to use a focus beam. I show it here defocusing. So the beam is now diverging as it goes through the material. And so the grating it creates will be a funny grating, a curved grating. It will be a zone plate, but a zone plate looked at from a little bit off axis. So the radiation diffracts, you know about how it diffracts. The radiation diffracts, and the radiation will diffract along a curve because the wavefront is curved. And if you think of the material, we're going to go and we're going to put a phase structure across the material. And that phase structure is a zone plate phase structure. So we create a zone plate in the material, a zone plate in the material by manipulating the electrons along the trajectory, modifying the phase just a little bit. This last time. I'm going to measure the zone plate. I'm going to do two things. So first I'm going to take this thing out, just look at a distance and look out here and say,